A lot of times pump selection or pump head calculation or pump hydraulic calculation has to be performed when you are working in MEP industry. Selection of pump means like the pump flow rate and the pump head has to be calculated. How much quantity of water the pump has to be delivered, that is called the pump flow rate. When the pump is recirculating the water or when it is delivering the water from the suction point to the delivery point, how much pressure losses it has to overcome, that is called the pump pressure. Pump pressure in terms of meter or feet is called the pump head. You should know different types of pump and their uses and selection. For example, HVAC, we are having like chilled water primary pump, secondary pump, tertiary pump, cooling tower pump. In district cooling plant, we are having heat exchanger pumps. In water supply, we will be having transfer pump, booster pump, hot water recirculation pump. Drainage, we are having like a sewage lifting pump. Then STP, we are having like a sewage treatment plant, we are having pumps. Irrigation, we are having irrigation pump. A lot of pumps are there. One in another way, the selection criteria is almost similar only, but we are having open loop and closed loop pump. Static head has to be taken into account when we are selecting the open loop pump. The same has to be neglected when you are selecting the closed loop pump. In this session, I will be selecting a transfer pump of water supply. The same will be transferring the water from underground tank to overhead tank. I'll be calculating the pump head or hydraulic calculation. Pump flow rate and pump head I will be calculating in this session. And after that, I will be selecting a technical data sheet. It means pump curve. From the pump curve, I will be selecting the model of pump. Okay, a project I will be including in this. Thank you. We can start. I have placed an underground tank and I have placed overhead tank as well, as per the actual dimension. Then we have placed a transfer pump. The transfer pump will be transferring the water from underground tank to overhead tank. So this pump we have to select. Transfer pump. Pump selection means pump flow rate you have to find. Pump head you have to find. Pump flow rate means the amount of water the pump is delivering. Means how much each second, how much liter of water, liter per second of pump has to be calculated. How much quantity of water, rate of flow of water the pump is delivering. That is called the pump flow rate. The second one, pump head. Pump head means simply nothing. From the suction, this is suction point, correct? From here, the pump will be taking the suction and this is a delivery point. From the suction to the delivery, what all losses the pump has to overcome. Then only the pump will be like the water will be reaching to the overhead tank, right? Pump pressure drop or pressure of pump, that is called a pump head. Both this value we should find. Pump flow rate. Transfer pump means, suppose this water supply transfer pump, right? Means water supply transfer pump will be transferring the water from this underground tank to the overhead tank. Underground tank to the overhead tank. So the transfer pump volume or pump flow rate is totally depending upon the tank it is filling. It is filling. So normally this transfer pump is filling the overhead tank, right? Overhead tank. So the transfer pump flow rate we can find. Transfer pump flow rate will be volume of tank to be filled divided by tank filling time in minute multiplied by 60. If you are using a pump to transfer the water from one location to another, that pump is called a transfer pump. For example, a drainage also we can use the same trend, but the purpose will be, suppose if you are having an underground drainage tank, from the underground drainage tank, if the water, rainwater has to be distributed, like expelled to some other location, that is called a drainage transfer pump. Water supply transfer pump will be filling the tank. Drainage transfer pump will be evacuating the tank. It will be taking water, right? Whatever it may, the selection criteria will be same only. The pump, it is transferring the water from one location to another. That is called a transfer pump. For underground transfer pump, for water supply, the transfer pump selection will be totally depending upon the tank it is filling. With once the overhead tank volume has 0, within how much time it has to completely refill that. Based on that, we can find it. So your transfer pump flow rate is equal to volume of tank to be filled. That is, tank to be filled means overhead tank. Volume of tank to be filled divided by tank filling time in minute multiplied by 60. Tank filling time, like as an average, like between 40 to 60 minutes you can select. Or even 20 to 60 minutes also you can use. As an average, like 60 minutes or 40 minutes is fine. Okay. Means any value between 40 minutes to 60 minutes you can use, but 40 minutes will be fine. Tank filling time. We have to decide it. If you are selecting tank filling time, you can imagine transfer pump should meet the peak requirement. Means if the overhead tank water level is decreasing at a rate of 1 liter per second, transfer pump should fill higher than 1 liter per second. On what rate the water level within the overhead tank is decreasing, higher than that rate, the transfer pump should refill that. Otherwise, suddenly people will be consuming all the water within the overhead tank. So it will be difficult to fill that again. So transfer pump flow rate should be meeting the peak requirement. As I told, peak requirement, maximum 60 liter only it will come. 40 to 60 liter. Per day, people might be consuming 135 liter or 180 liter or 200 liter. Out of this 200 liter, people might be consuming maximum quantity of water in the morning time, peak time. How much it will come? Nearly 30% of per day demand. 60 liter it can come. That 60 liter within how much time, within how many time or they will be consuming? People might be waking up at 7 a.m. and they will be going to office, let's say 8 a.m. Between that 1 hour, between that 60 minutes, people will be consuming, each person will be consuming nearly 60 liter of water. So if people are consuming 60 liter of water within 1 hour, the same 60 liter of water transfer pump should fill less time. Means people will be taking 60 liter of water with a 60 minute. Transfer pump should fill the water on a higher rate, right? Otherwise, the tank volume will be decreasing soon. That's why tank filling time, 40 to 60 minutes you can consider. As an average, you can select 40 minutes for tank filling. Okay, so yesterday we have calculated the overhead tank volume. I'm just going to calculate the transfer pump volume. Transfer pump volume will be volume of tank to be filled. What's the volume of tank? This one. That is 6 meter cube. Overhead tank, the volume will be 6 meter cube. 6 meter cube is how much? Volume of tank to be filled is 6 meter cube. That is 6,000 liter. 6,000 liter only. Okay, this is it. Liter. Tank filling or evacuation time, 40 to 60 minutes you can take. Tank filling time as an average, I'll be selecting 40 minutes. Now, what about the pump flow rate? The transfer pump flow rate is equal to volume of tank to be filled divided by tank filling time in minute. So you'll be getting the value in liter per minute. Multiplied by 60, you can convert that into liter per second. So the pump flow rate, how much we will get? 2.5 liter per second. Correct. 6,000 divided by 40 into 60 by this equation. The pump flow rate will be 6,000 liter per second. How much gallon per second it can come? 1 gallon is equal to 3.78 liter. So liter per second divided by 3.78, you can convert that into gallons per second. Gallons per second multiplied by 60, you will be getting that in gallon per minute. In chilled water, we already did that. So gallon per second multiplied by 60, you'll be getting that in gallons per minute. So transfer pump flow rate will be 2.5 liter of water in each second or 39.68 gallons per minute. That one we can select. Okay. The next step. So we have calculated the pump flow rate. The next step, this transfer pipe diameter we should find. Now it is clear that nearly 2.5 liter of water we are distributing by this way. But we know the GPM. By the help of pipe sizer, we can find it. I'm just selecting the pipe sizer. Like pipe sizer, let me select it. Okay. So water supply only. So I'll be selecting schedule 40 PVC plastic. Water temperature 70 degree Fahrenheit. Okay. What diameter we need? This condition you should maintain. The same condition, water supply pipe sizing already we do. Up to 2-inch dia pipe, 1.8 meter per second or 4 feet per second. Even if you can go up to maximum 4.2 feet per second as a boundary. About 2-inch pipe means 65 mm onwards, you should Maximum velocity should be 2.4 meter per second or 8 feet per second. What should be the pipe diameter, let's say? Anyhow, the flow rate will be 39.68 GPM. Anyhow, half inch is not possible. 39 means try for 1.5 inch. 1.5 inch pipe. 1.5 inch pipe. We are trying to deliver 39.68 GPM. 39.68. 39.68. Yeah, pipe diameter less than 2 inch. Less than or equal to 2 inch. The velocity should be less than 4 feet per second. And here it is coming 6.25 feet per second. So not possible, right? You can go for next one. 2 inch pipe. 2 inch pipe 39.68. Yes, this is fine. 2 inch pipe 39.68 US GPM. Pipe diameter is fine because fluid velocity is getting 3.79. You can go up to 4 feet per second. Even if as a boundary of 4.2 feet per second, leave it, no problem. And select 39.68. Fluid velocity 3.79. The pipe diameter will be 2 inches. Okay. So diameter of pipe is 2 inches. Head loss we need because for the pump head calculation, we need head loss. What head loss we are getting? Here you can see head loss will be 2.6 feet per 100 feet. How much Pascal per meter it can come? 2.6 feet per 100 feet. How much Pascal it can come? Feet per 100 feet multiplied by 100, you will be getting that in Pascal per meter approximately. 2.6 feet per 100 feet is 260 Pascal per meter. 260 Pascal per meter. So that's why here we are getting 2.6. No, that we should take. Head loss will be 2.6. 2.602. 2.6 feet per 100 feet. How much Pascal per meter it can come? That is feet per 100 feet multiplied by 100. You can convert that into Pascal per meter. But actual how much, as I told, feet per 100 feet multiplied by 100, you'll be getting that in Pascal per meter. So 2.6 feet per 100 feet is nearly 260 Pascal per meter, 260. But accurately, that is approximate value only. Accurately, we can find it. We can find it. Means it's clear that here the head loss they are mentioning in each 100 feet of pipe length, 2.6 feet of pressure drop, water column. 2.6 feet or meter, that is in pressure drop only, that is in terms of water column. 2.6 feet per 100 feet. Okay. So you can see length of pipe is 100 feet. Loss will be 2.6. So each 100 feet of pipe length, 2.6 feet of pressure drop can come. I'm doing my head loss calculation, everything in Pascals per meter, SI unit. Pascals per meter means this is each 100 meter of pipe length, 2.6 feet of water column pressure drop can come. I need the pressure drop in Pascals per meter. Each meter of pipe length, how much Pascal of head loss can come? Correct. So I have to convert that into meter. How you can? 1 meter is equal to 3.28 feet. 1 meter is equal to 3.28 feet. In the basics, we have discussed that. So this feet you can convert into meter. Means this value divided by 3.28, it will be converting into meter. This value divided by 3.28. So 100 feet means 2.6 feet per 100 feet is equal to 0.79 meter per 30.48 meter of pipe. Means feet we have converted into meter. Each 30.48 meter of pipe length, 0.79 meter of water column pressure drop can come. But now also the pipe length is not unit meter. That is 30.48 meter only. I need per meter because head loss I should calculate in Pascals per meter. Per meter flow rate I need. Sorry, per meter calculation. This is each 30.48 only. So what we can do? So loss divided by length of pipe. Each 30.48 meter, 0.79 meter. So 0.79 divided by 30.48, 1 meter pressure drop we can find. So each meter of pipe length, 0.026 Pascal, 0.026 meter of water column pressure drop can come. Each meter of pipe length, 0.026 meter of water column pressure drop can come.
I need that in pascals. See, we are having an equation. Pressure is equal to density into gravity into water column. From this equation, P is in the pressure or loss in Pascal. We have to find that one. Rho is density of fluid. What fluid we are doing? We are dealing water. So density of water will be 1000 kilogram per meter cube. P is equal to rho GH. G is acceleration due to gravity. The value will be 9.81 meter per second square. H is pressure loss or head loss in meter. This only we found that. So this is H value. If you know H, you can multiply with the density and gravity. You can find P. P is equal to rho into G into H. Okay. So it is clear that when we are sizing from the pipe sizer, we got 2.6 feet per 100 feet. Correct. Means each 100 feet of pipe length, 2.6 feet of water column pressure drop can come. We have converted that into meter. So 100 feet of pipe is 30.48 meter of pipe. So each 30.48 meter of pipe length, we are having 0.79 meter of water column pressure drop. But we need the pressure drop in Pascal per meter, 1 meter pressure drop. So loss divided by length of pipe, 0.79 divided by 30.48. Each meter of pipe length, 0.026 meter of water column will come. This is H. So from this equation, you can find it. Now the pressure drop will be, your pressure drop is equal to rho GH. Rho is 1000. G is 9.81. H is this one. So actually 2.6 feet per 100 feet is how much? I told 2.6 feet per 100 feet. As a thumb rule, 2.6 feet per 100 feet multiplied by 100, you'll be getting 260 pascals per meter. Means feet per 100 feet multiplied by 100, you can convert that into Pascal per meter. But that is not 100% accurate. Accurately, 2.6 feet per 100 feet is how much Pascal per meter? That is not 260 Pascal per meter. That is it. That is 255 Pascal per meter. How much Pascal difference? Just 5 Pascals difference. 5 Pascals difference. 1 bar of pressure is equal to 1 lakh Pascal. 1 lakh Pascal. This is just a 5 Pascal difference. Correct. So it is not mandatory to do like this, but if you are doing this, just for your knowledge, I have converted that. Even if the feet per 100 feet multiplied by 100, that head loss you can use for your calculation. But this is accurate value. That's why I will be following this 255. Okay, both you can follow. So how much we will get head loss when we are designing for 2-inch pipe, 39.68 GPM. The head loss will be 255.06. Let's say 255 Pascal per meter. I got this. So we found the pump flow rate, we found the diameter of pipe, we found the pressure drop. Now we can go for hydraulic calculation. Means if you want to find the pump pressure, what is pump pressure or pump head means? From the suction to the delivery, what all losses the pump has to overcome? The first thing, the pump has to overcome the material loss. What all losses the pump has to overcome from suction to delivery? The first one, material loss. Material loss, we are using PVC pipe or whatever the pipe material it may. No material is having 100% smooth, right? Every material is having surface roughness. Due to the surface roughness, frictional losses will come. Pump has to overcome that. So material losses is a reason. How we can calculate? Material loss, we know already the head loss. Pascals per meter. Each meter of pipe length, 255 Pascal of pressure drop can come. Now from suction to the delivery, total horizontal plus vertical, how much meter of pipe? Suppose 30 meter of pipe, means 1 meter, 255 Pascal. 30 meter, 30 into 255 Pascal. Accordingly, you can find the material loss. Okay, we'll do that. The next one, fittings loss. Fittings loss with respect to the equivalent length, we have to do that. From IPC, we'll be doing it. IPC table, we'll be taking the data for that. The third one, static head. Means from the suction to the delivery, it has to overcome the gravity. That we have to overcome. The fourth one, a residual pressure. After overcoming all the pressure drop, how much balance pressure has to be maintained at the delivery side? That is called residual pressure. I will explain that. These are the 4 important losses we should consider. Residual is not a loss. We have to consider that. Anyhow, we can start with the first one, material loss. Material loss that is due to the surface roughness of the pipe material. You can calculate using this equation. Material loss is equal to length of pipe multiplied by head loss used for design. Head loss used for design, we know 255 Pascal per meter. 1 meter pipe length, 255 Pascal of pressure drop. Like that, some suction to the delivery, how much meter it can come. Okay, length of pipe overall. Okay, so I need horizontal length of pipe separately. Horizontal length of pipe separately. Vertical length of pipe separately. This is like a total horizontal length of pipe, total vertical length of pipe. Okay, how much meter it can come? We should find. Anyhow, this length of pipe we can take from the root only. I'm just going to the drawing. Horizontal length I should take first. This one. Anyhow, along with the pump, we can take from here to here. How much that is? 3325.7. This is in millimeter only, but I need that in meter. 3.3 meter. Okay, 3.3 meter here. Then here in the roof side. From the center you can take, or even if you're taking from here, that is fine. This one. And from this point to this point. Overall, how much? See, first this one. 3.325. Total horizontal length will be 3.325 plus the remaining horizontal is in the roof. 1.380 meter. 1.380 plus then this one 7.732 plus 7.732. How much it is? 12.437. That is horizontal. We need vertical as well. Okay, this is horizontal. Vertical we can take from the section or riser diagram. This, because the height is actual dimension. So this vertical you can take from here. Overall vertical. Horizontal we have already taken. These are horizontals only. Vertical from this point to this point. Total vertical. Correct. From here to here, then from here until here. Overall, if you're adding this plus, the same only you will get. How much it is? 24.25. 24.25. Keep it there. So that is 24.25. That's a total vertical. So total length of pipe, how much you will get? Total length of pipe is horizontal plus vertical. Horizontal 12.43 plus vertical is this one, 24.25. Length of pipe will be 36.68 meter. Okay. Now the head loss used for design, we already know head loss used for design is this much Pascals per meter. This much Pascals per meter. Now the material loss will be, material loss is length of total length of pipe. Length of pipe is this much. Multiplied by head loss used for design is this much. So total material loss will be 9,355 Pascal. 0.9 bar. 0.09 bar. That's our material loss. The next one, fittings loss. The pipe diameter is 2 inch only. 2 inch dia pipe. Fittings loss, how we can calculate? Fittings loss we will be calculating as per, see, as a thumb rule. 50% of the material loss we can consider as fittings loss. For example, material loss is 9,355. This value multiplied by 0.5. Fittings loss you can consider 4,677. Half the length of pipe. But that is not accurate. Correct. That is not accurate. So I should calculate this one. See, I'm just going to create isometric layout of this one. Means isometric layout of this. From the isometric layout, I can find it. So how to prepare this isometric layout? Okay. See, anyhow, I'm just having this pump I am taking. It is not mandatory to make the isometric layout to find the fitting, but let me make it. Because this is a horizontal and vertical, you'll be having what type of fittings will come, you might be having doubt. Isometric layout. Now, to draw the isometric, you should select isometric screen. You can come to the options for snap settings. From the snap settings, instead of a rectangular snap, you have to activate this isometric snap. Select this one. Okay. Now you can take your line. See, the pipe will be going this way. Correct. But if the path has to be changed, you can use function key F5. When you are selecting function key F5, now the mouse pointer is going this side. It is going this way. Upside and downside is restricted. Again, the function key F5 you can activate. Then it is going up and down this way. But here also you can change isometric screen. ISO plane left. ISO plane top. Here also you can change it, right? But F5 is the easy key. Okay. So anyhow, let me take it. First one is coming from the top. What's the height of this one? Suction. This is like a 3,152. 3,152, let's say. So I'll be making a vertical line of 3,152. From here, 3,152. Yes. Vertical, suction line. Now from there, it is going right side. From there, it is going right side. Correct. What's the length there? There we are having 1,392. 1,392. So from this point, I'll be making my pipe like this. 1,392, 1,392, and there. Okay. Here I'll be having my pump. Okay. Pump, it is not mandatory to use this one. You can use this as well. Okay. Just the representation we need. Anyhow, or I will be aligning this one. Align. First source point, first destination point, second source point, second destination point, enter. Okay. This is my pump. There is my pump suction, correct. And move it. So pump will be taking the suction from there. But you can make your pump straight. But I'm keeping. You can make your. It is not mandatory to place this one like this. If you want to make it straight, you can do that. I guess this is inclined. It is not good. Okay. You can place the same. And that also you can place, no problem. But again, we have to rotate it and all this will be easy. So that is your pump suction. Now from here, pump will be delivering the water. So correct, horizontal also you have to check. Then vertically, little bit the water is coming this vertical. So from here to here, that will be 2.87 means 287 millimeter means 0.287. So from the pump approximately from here, let's say approximately from somewhere here or even from the top side, it's not a big issue. 0.287. Vertical it is 0.287. Vertical it is rising up. 0.287. Vertical it has to rise up. Who's more? Ah, this is millimeter only, no, 287 millimeter. I'm making in meter. Okay, I fade out. 287 millimeter vertically. Then it is going this way. Correct. This one. You can take the measurement either from here or you can take from here as well. Means from the pump, it is going near to the shaft. How much it can come? From here to here, that is 2128. 2128. That is going this way. (2128) that is going like this. From this point, it has to vertically go upside. Correct. Suction up to the pump. From the pump, the vertical. Then it is going to the shaft. From now, this is to the shaft only. From the shaft, it has to vertically rise upside. See, isometric Lloyd preparation is not mandatory for MEP. Oil and gas normally, but sometimes it might be asking at the time of interview. There is one company called Goignis. Goignis, a lot of Delhi company only. A lot of my students are working there. So normally that company used to give this isometric task. Okay. So this is how much it is. 18,932 vertical height. So from this point, 18,932 vertically it has to rise upside. 18,932 vertically that is going upside. Now that has reached here. Here, where? Here. You should not take this way because this one you should consider horizontal. Because this line is not there in the vertical. From vertical, you will be witnessing this one. This side view. But this you should not avoid. So that's why the distance is how much? Getting like 1380. So from this point, 1380, it will be coming this way. F5, this way. 1380. From there, it is going this side. Correct. Now, from this point, it is going this way. This one. That one you can take the length from here. That is 7424. 7424. So from this point, that will be 7424. 7424. Okay. Now it has reached just to bottom of tank. Now it has to vertically rise upside. From this point, vertically it has to rise upside 1760, 1750. So from here, 1750, then it is reaching to the tank, this line. See how much it can come. 362 millimeter. So from there, that will be 362 millimeter. This is my isometric route. So total horizontal and vertical is there now. So from this route, we can find from the suction to the delivery, what all fittings will come. Fittings means elbow, T-joint, correct, elbow joints, T-joints, then valve, everything can come. Anyhow, see when we are placing the pump, this is your underground tank. Okay. This is a water level. If the pump has placed above the water level, then this suction pipe we have to fill with the water. Because inside the pipe, air should not be there. Because density of air is 1.2 kilogram per meter cube. Density of water is 1000 kilogram per meter cube. So pump air will not be able to suck it. That's why if the pump has located above the water level, that is called negative suction condition. Negative suction condition, suction pipe we have to fill with the water. That process is called priming. Priming has to be done for negative suction. And also, you have to make sure that once we are filling the water within the priming this one, filling the water in the suction pipe, it should not go back to the tank. So here, for negative suction pump, there we will be providing a valve that is called a foot valve. Foot valve is a unidirectional valve that will allow the water to flow only one side. Water will be flowing only this side. Water will not be coming back to the tank again. Okay. That's why negative suction means if the pump has located above the water level, in the suction pipe, we have to fill with the water to adjust the density difference. We have to fill with. So if you are filling with the water inside the suction pipe and the water liquid has to be raised is also same fluid. So density will be same. No? That's why we are doing the priming. So, but after filling it, if the pump is not working, means the water column that it is existing within the suction pipe should not go to the tank or the well. That's why we will be providing a valve called a foot valve. Pump foot valve. It will allow the water to flow only one side. This one. So this is your suction pipe. We'll be filling water. Here you can see this is normal position, closed only. But if the pump is working, means this diaphragm, no, or this diaphragm will be rising upside. The water will be flowing up. The pump stop. There is no suction. So then automatically it will be coming down by the help of a spring force. Then it will close. So this will only allow the water to flow upside when the pump is working. Water will not be flowing backside. So in the suction side, in the bottom, we will be connecting it here. You can see. This is a pump. Correct. Base will be providing a foot valve. Here you can see the pump has placed above the water level. Okay. So that's why negative suction cases, priming has to be done. But if this is your tank, pump has located here. And pump is delivering like this. Here, water level is upside of the suction. This is called a positive suction. Means the pump located within the water, submersible pump, or the water level is below the pump suction. Water level is above the pump. That is called the positive suction. Positive suction, you don't want to do priming. Priming is not mandatory because always in the suction line, we are having water by gravity. Positive suction, foot valve is not mandatory. Foot valve is not mandatory. But a strainer has to be provided. A strainer means contamination, dirt should not enter into the pump body. So that's why a strainer like this, a strainer has to be proposed. So contamination should not enter into it. Foot valve is not mandatory. So that's why here in this side, when you are considering this loop, here we will be having a foot valve because this is positive, negative suction only. Pump is located upside. Here we will be having elbow because this is one pipe, vertical pipe, and it is going like this, 90 degree. 90 degree we can use in water supply. So here we will be having 90 degree elbow. Okay. So how much elbow can come? Elbow 1, 2 here. Here also we are having no second elbow. 3, 4, 5, 6, 7. 7 numbers of elbow can come. This is 90 degree pipe elbow if you want to take the directional change. Correct. First elbow, second, third, fourth, fifth, sixth, 7 number of elbow will come. It is not mandatory to make the isometric layout in the plan itself. You can assume that, but if you are making the isometric layout, you will not miss the fitting. And also when it is reaching here, means when the water has reaching to the top side, here, like this it will come. This is your pipe. Then water will be, if the water velocity is too high, water will be hitting on the side wall of your tank. Water will be hitting on the side wall of your tank. How we can avoid that? See, when it is coming there, the pipe will be coming from the bottom like this. Then it is entering there. There you can provide a T-joint like this. A T-joint you can provide. So water will be flowing downwards rather going this way. Water will be flowing downwards. Then after the T-joint, we will be slightly extending the pipe. Then we can propose an end cap there. By the help of end cap, we can close it. So a T-joint you can provide. Otherwise, your pipe will be coming there. There you can propose an elbow. If you are proposing an elbow there, right, elbow here, water will be flowing down only, not there. Because anyhow, since the R-headed tank, since we are having a transfer pump, we don't want any float there. If you're having float, it is not mandatory. Float is another fitting. Float you have to consider another fitting. But for this case, this is float operated, float switch operated valve only. So we don't want any float valve there. Because the transfer pump will be automatically starting and like operation. So that's why here one more elbow I'll be considering. So number of fittings I should consider. The first one, 90-degree elbow. How much can come? 90-degree elbow. 7 number in the root. 7 number in the root. 1 number here I am considering. 8 numbers. 2-inch quantity elbow, 8 numbers. The next one, foot valve. Foot valve is an NRV, non-return valve. 1 number in the section. Any other valve? See, some standard, for every pump, some standard fittings are there. Standard. So that is common for almost all the pump. Pump suction side and the pump delivery side. So anyhow, if it's a negative suction, foot valve will come. Positive suction, only strainer. But normally for standard pump, if it is pump suction line, pump delivery line. Always suction line starting, delivery line end will be having 2 number of isolation valve. Isolation valve means gate valve we can propose now. Gate valve is there, ball valve is there, sluice valve is there. Pump line and all, gate valve only normally we are using, gate valve. Why? In any case of emergency, if you want to isolate the line, you can close this isolation valve. Pump you can remove and you can do the maintenance. Always in the suction side, we will be having a strainer valve. Strainer means the contaminations should not enter into the pump. That's why we will be proposing pump strainer valve. This one. So this strainer valve, you can see when the water will be flowing through the strainer valve, the contamination will be accumulated on the bottom. You can open the flange, periodically you can change it. If you are not properly cleaning your strainer, block will come, so that will be affecting the performance. So that's why pump suction line will be proposing strainer valve, so that will be increasing the load. Always in the pump delivery line, there we will be having an NRV, non-return valve. NRV, check valve, feed check valve, unidirectional valve, same name. That will allow to deliver the water in only one side. Water will not be coming back. Why? You can see the pump will start. The pump will start delivering the water until here. All in a sudden, if the pump stop means water we are having in the vertical column, vertical line will be coming back to the tank again. That has to be prevented, right? Means water should not come back to the tank again. Then pump has to again work. Correct. That's why the pump delivery side always will be having NRV. Okay. The next one, in the strainer line, after the strainer, NRV, we'll be having flexible, okay, pipe connector, flexible pipe connector, and a union also will come, union to connect it. Flexible pipe connector. Why? Because pipe is rigidly fixed, pump as well. So if you want to connect that properly, you need some allowance. So it means flexibility should be there, no? That's one reason. The second one, when the pump is working, the vibrations should not transfer to the pipe. That also we'll be using this flexible pipe connector. Rubber only or neoprene. Flexible pipe connector, this one. But fittings loss of this one is negligible. You don't want to consider that. Okay. This is for to isolate vibration. Another fitting is conditional. Means, as you know, in our case, suction and delivery, the pipe diameter is 2 inches only. But it doesn't mean that manufacturer, this pump inlet and outlet diameter is always as per our requirement. Our diameter is totally depending upon our flow rate. But when we are selecting the pump from the technical data sheet, in real scenario, pipe diameter that we have designed and the manufacturer machine inlet outlet diameter will be varying. Okay. So that's why if suction line and delivery line, if our designed pipe diameter and the pump diameter, pump inlet and outlet connection is matching, means you don't want that fitting. Otherwise, always in the suction, you need an eccentric reducer. Delivery, you need a concentric reducer. Because pipe diameter is not matching, means we have to provide the taper section. No. Pipe, eccentric and concentric reducer. Eccentric means this one. Correct. One side will be straight, other will be changed. Concentric is this much. Why in the suction side eccentric, delivery side concentric? Most of the case, this will come reverse, means this will be coming like this only. Means manufacturer pump inlet will be less than our requirement. Less than. So a reducer piece will come, but that will be eccentrically. Why? Otherwise, why we are proposing this eccentric reducer in the suction side? There is an effect called vortex effect. Due to the suctional velocity, sometimes water will be rotating there. The vortex effect will be creating. The vortex effect has created, air bubbles will be trapping inside. So that will affect the performance of the system. Air bubbles is creating means the air bubbles will burst. Whenever the air bubbles are bursting means it will be eroding the pipe material and the pump material, correct? That effect is called cavitation. That's why this vortex effect will enhance a process called cavitation. Cavitation, there is other reason as well that we can discuss. So that's why suction side eccentric reducer, delivery side concentric reducer we will be proposing. So these are the standard fittings. What all fittings you should consider? These two IV, strainer and NRV. Fine. Other fittings you can neglect. Okay. Two isolation valve. Okay. So let me select it for safety. If you want in the top side somewhere here, because isolation valve, we are providing one number here and another one here only. For safety, if you want to isolate the entire line, because water will be flowing from there, no? In any case, if you want to close the water, if you want to remove the tank, or if you want to do some maintenance, if you want to close the water, from somewhere in the delivery side, in the roof side, here also you can propose a gate valve. Okay. So that's why the next one, isolation valve or gate valve. One number in the pump section, one number in the pump delivery, one number for safety in the roof side. 3 number, maintenance. Non-return valve, NRV. Pump delivery, 1 number. Strainer valve, pump suction, 1 number. These are the fittings we are having in the room. Due to these fittings, definitely the pressure drop will come. Correct. When the water is flowing through the fittings, due to the profile of fittings, pressure drop can come. How we can calculate? Fittings loss we will be calculating with respect to the top equivalent length of pipe. Equivalent length concept means, see, I have designed a 2-inch dia pipe. Pipe diameter is 2 inch. Head losses is 250 Pascal per meter. So I'm having a pipe material. The length of pipe material is 2 meters. Okay. So water will be entering at this region, position number 1. And it is having like 1,250 Pascal of pressure. When it is leaving, how much pressure can come? Anyhow, head loss is how much? 250. Each meter of 1 meter pipe length, 250 Pascal. 2 meter pipe length, the loss will be 2 into 250 Pascal. 1 meter, 250. 2 meter, 2 into 250. So loss will be 500 Pascal. So the available pressure at the outlet will be 1,250 minus 500. 750 Pascal will be available in the other side. Clear? The same way, in the same route, I am having an elbow. 2-inch dia, 90-degree elbow. But it is not having 2 meter length. It is very small only. See, when it is entering, it is having a pressure of 1250. When it is leaving, I'm not using that, the example, it is having just a 750 Pascal of. So nearly 500 Pascal of loss Pascal. Correct. When it is entering 1250, when it is leaving 750 Pascal only will be available because 500 Pascal of pressure drop has happened within this elbow joint. Now I can say a single elbow for this system is equal to 2 meter of pipe length, straight pipe length. One elbow is equal to, because pressure drop that is happening in 2-meter pipe and the pressure drop happening that is in a same diameter elbow, then I can say one elbow is equal to 2 meter of straight pipe. So elbow you can equate into the length of straight pipe. That is called equivalent length. Every fitting is having equivalent length. Equivalent length. So that equivalent length from the Google, or you can search it. IPC also has provided. IPC is also there. So I'm just going to the International Plumbing Code and I'll be finding the equivalent length. Okay. Equivalent length of each and every fittings we can take. International Plumbing. Sorry. So like a page number. PDF page number 166. Table number this one. PDF page number 166. Allowance in equivalent length of pipe for frictional loss in valves and threaded fitting. Threaded fittings only this one. And this will be valves, pressure drop in fittings, equivalent length in feet only, but that is for tube fitting. Means pipe threaded fitting means screwed fitting. This one. Screwed fittings will be used. Normally, valve connections will be, even if we are using PVC pipe. PVC pipes are normally not screwed fitting. PVC pipes are solvent welded only. Okay. So that's why, like, for example, gate valve. Gate valve, all kind of valve is a threaded connection only. Valves are threaded fittings. But normally, like a UPVC pipe or CPVC pipe, whatever it may, those are solvent welded only. By the help of pipe joints, we can use. So when you are dealing with the valves, all kind of valve data, you can take equivalent length from here. Other straight pipe, elbow, T-joint, for PVC pipe, we can take. Tube fitting means solvent welded. This will be threaded. Valve will be threaded. So data you can take from here. Okay, anyhow, the first one. Elbow. What might be the equivalent length of 90-degree elbow? I need that in meter because I'm doing an essay. But in IPC, they have provided that in feet. 2-inch diameter pipe. Pipe diameter is how much? 2-inch dia only. 2-inch dia pipe. Nominal pipe diameter. Fittings loss in feet. Pipe diameter 2 inches. Standard elbow 90-degree, 45-degree. 90-degree. This is T-joint only. T-joint side branch straight run. Means, for example, if you are having a straight pipe, this is your T-joint. Side branch is this one. Straight pipe is this one. If you are doing the loss calculation for straight T, this one you have to select. Side branch, this one you have to select. Anyhow, we are dealing with elbow only, standard elbow 90-degree. 90-degree standard elbow is equal to 5.5 feet of straight pipe. One elbow is equal to 5.5, means loss that is happening in a 2-inch dia, 90-degree elbow is equal to 5.5 feet of straight pipe. Okay, that one you can take. Equivalent length is equal to elbow 90-degree, how much it is? 5.5 feet, but I need that in meter. Feet divided by 3.28, you can convert that in meter. Feet divided by 3.28, so one elbow is equal to 1.67 meter of pipeline. Okay. Like that, how much elbow we are having? One elbow is equal to 1.67. We are having 8 elbow. So total equivalent length will be 8 into this much. Total 13.41 meter of straight pipe. Head loss is how much? Head loss is 255 Pascal per meter. Correct. This for this. Head loss is equal to 255. Pascal per meter head loss. Loss will be total equivalent length of pipe into head loss used to 47. One elbow, 1.67 meter. Like that, 8 elbow, 13 point. Loss will be 13.41 multiplied by 250. 3420 Pascal. That much will come for elbow. 13.41 multiplied by 250. That is elbow. IV, isolation valve. Gate valve you can consider. Valve should be a threaded fitting. You can take the data from here. Gate valve you can take. Threaded fitting. Gate valve. 2-inch dia pipe. 2-inch dia gate valve. The pressure drop is 1.3 feet of straight pipe. 1.3 feet. So equivalent length in meter will be 1.3 feet only divided by 3.28. You'll be getting that in meter. Rest everything is same. So like that, one IV is 0.339 meter equivalent length. Like that, 3 IV, 3 into 0.39, it will be 1.18. 1.18 into 255, we'll be getting 303 Pascal of pressure. That is for elbow. Non-return valve. Non-return valve, check valve, swing check valve, feed check valve, unidirectional valve. Different name we are having. Valve, NRV. Here you can see check valve, this one. Non-return valve. So 2-inch dia, check valve is equal to 22.4 feet of straight pipe. High pressure drop will come. Unidirectional valve, it will allow water to flow in one side. Backflow it will prevent. One NRV is equal to 20. Foot valve also you can consider the same. Strainer also the same only. Because you can see strainer there is nothing. Strainer data normally we should take from the manufacturer catalog. If it is not there, the same check valve loss you can consider strainer. 22.4. So you can see NRV will be 22.4. So 22.4 feet divided by 3.28, that will be 6.8. So remaining also. Strainer loss, the same NRV loss you can consider as strainer because similar. Foot valve is also an NRV, non-return valve only, the same you can consider there. So overall fittings loss you'll be getting. You can add all these things. How much you will get? This will. You can add. See the formula. We are adding it. 8,948 Pascal. Somewhat near to material loss it is coming. Sometimes it will go beyond that. So 50% of material loss, if you are considering as fittings loss, that will not be always correct. That is our fittings loss. So we have calculated material loss and we have calculated fittings loss as well. The third one, static head. Static head means from the suction to the delivery, how much gravity it has to overcome. Total vertical height. From the suction to the delivery, total vertical height. So gravity, static head, you can consider the same equation. P is equal to rho into G into H. Rho is 1000 kilogram per meter cube. G is acceleration due to gravity, 9.81 meter per second square. H is pump head or pump total vertical height in meter. Vertical height in meter plus suction plus delivery. From this equation, you can find how much gravity the pump has to overcome. Suction to the delivery. There is no suction, only the delivery has to be considered. Normally for negative suction pipe will come, delivery pipe will come. From the suction to the delivery, overall vertical height is the total. But for positive suction pump, suction will be 0, only the delivery will come. Positive suction, we don't want to do priming, right? Because pump will be located below the water level. So positive suction pump, normally delivery pipe will not come. Suction pipe will not come, only the delivery will come. Okay. Anyhow, total vertical height, suction plus delivery, we have already taken that. Total vertical height, suction plus delivery, total vertical length is 24.25. Correct. Means from suction to the delivery, total vertical This up to here, that is suction. Then from here to here, that is delivery. Anyhow, total suction plus delivery up to the tank, it is 24.25 meter. So this much vertical height, the pump has to overcome the gravity. That is called a static head. Static head. So come here. How much we are getting static head? Total vertical height, suction plus delivery 24.5. Now from this equation. Okay. From this equation, you can find like P is equal to rho GH. Rho is 1000. G is 9.81. H is equal to 24.25. So nearly 2,37,892 Pascal. Comparing to all the other laws, normally static head will be the high laws. Okay. So static head also we have to calculate. We have calculated. The next one, residual pressure. Residual pressure. If the pump is able to overcome all the other three drop, material, fittings, and the static head, water will be reaching up to this point. But we need some extra push, extra velocity we need. That velocity or that pressure is called residual pressure. You can say firefighting hose is having high residual pressure. After overcoming all the pressure drop, the tip of nozzle, we are having very high velocity. That's why the water will be traveling to a larger extent. That's why residual pressure, after overcoming all the pressure drop, pressure that is available at the tip of pipe, that is called residual pressure. Normally, the residual pressure has to be calculated for 1.8 meter per second velocity. But this is velocity. No? Pressure that is equal to 1.8 meter per second, that only we record. Correct. For how much it can come? 1.8 meter per second velocity, if you need as a balance pressure, you can calculate. Velocity is 1.8 meter per second. Okay. So we are having an equation equivalent to 1.8 meter per second. What should be the pressure there? That is called the velocity head. We can find if the velocity is 1.8 meters per second, corresponding to 1.8 meter per second, the velocity pressure will be V square by 2G. V square by 2G. V square by 2G means 1.8 into 1.8 divided by 2 into 9.81. From this calculation, you can find the velocity head in meter. Okay, how much it will come? V square by 2G. So our velocity we need 1.8 meter per second. So velocity pressure will be, or velocity head will be V square by 2G. V 1.8, V into V square divided by V square by 2G. 2 into 9.81, acceleration due to gravity. So 1.8 meter per second is equal to 0.165 meter of water column. This is H only, velocity head. Now this head you have to convert into Pascal. P is equal to rho GH. H you know. Now the Pascal, if you want to find 1000 into rho into G into 9.81 into H, we got there. How much Pascal? 1620 Pascal. That's why normally for 1.8 meter per second of residual velocity you need in the tip of pipe, you just have to consider 1620 Pascal of pressure, residual pressure. That only required. But normally, design engineers will be considering a residual pressure of 5000 to 10,000 Pascal. As you know, 5000, 10,000 Pascal is not mandatory. Just 2000 Pascal is also fine if you are considering. Anyhow, normally, generally, we'll be considering 5000 Pascal, even that is also fine. So we'll be considering residual pressure 5000 to 10,000. I'll be considering 5000 Pascal there. Okay. So we have considered all the four losses. Now you can calculate actual loss. Your actual loss will be your material loss plus fittings loss plus static plus residual. Correct. So how much it can come? That will be this much. 2,61,196. This much Pascal of pressure drop can come. But even though when we are selecting a fan or when we are selecting a pump, safety factors has to be considered slightly extra. 5 to 15%, but 10%. If your input, if you're perfectly everything, all the fittings correctly, if you are doing means 10% or 5% safety is more than fine. So I'll be considering 10% safety. So my safety factor will be 10%. 10% extra I'll be considering. So this value, actual loss into 1.1, you'll be getting the total loss. actual loss into 1.1, you can find the total loss. But if you are doing in Excel, total loss will be actual loss plus 10% of actual. This value multiplied by this value into this one, 10%. So if it is increasing, accordingly, the total loss will increase. But we need just 10%. This much. So that is your total loss in Pascal. But as I told, we need pump head. Pump head in meter or pump head in feet. We need the pump pressure not in Pascal. Pascal, that is fine, but we have to calculate that in meter as well or in feet. You know, the equation P is equal to rho into G into H. P we are having there. Rho we know 1000, G is 9.81, H we have to find. H is equal to P by rho G. H is equal to P divided by rho G. Means your total loss divided by 1000 into 9.81, you can find the pump head. Same equation you should apply. So your pump head will be P by rho G. P is this one divided by rho is 1000, G is 9.8. The pump head is equal to 29.28 meter. 29.28 meter. Okay, fine. Now our selection will be the pump flow rate. Our selection will be pump flow rate is 2.5 liter per second. So selection 2.5 liter per second. At how much meter of head? 29.28. Let's say 29.3. Pump head is this one, 29.28. So that is 29.3 meter of head. That is our selection. Clear? So to select the pump, only the flow rate and head you required. But pump power also we can calculate. Power of pump also we can calculate. Power of pump, but it will vary with respect to the actual efficiency of machine. Power of pump in kilowatt. Pump power in kilowatt. It is not electrical consumption. Because how the pump is delivering the water? Pump is having an impeller. How the impeller is rotating? We are having an electrical motor. Electrical motor is having a shaft. The shaft will be connecting to the impeller. So when the motor is rotating, the shaft will rotate. Accordingly, the impeller will rotate. So what is the shaft power to rotate the impeller? Not the motor efficiency, not the motor power. We will be calculating the hydraulic, mechanical power only. Okay. So power in kilowatt of mechanical power in kilowatt or shaft power is equal to rho into G into Q into H divided by 1000 into efficiency. This is eta, efficiency. From this equation, power of pump in kilowatt, rho is density of what fluid you are dealing. If you are using water, then density will be 1000 kilogram per meter cube. G, acceleration due to gravity. Acceleration due to gravity, that will be like 9.81 meter per second square. Q is pump flow rate. Pump flow rate not in liter per second. You have to take care. Pump flow rate in meter cube per second. You need pump flow rate in meter cube per second. H is equal to pump head in meter. We have calculated 29 this way. Pump head in meter. 1000 is for conversion. Eta, efficiency of pump will be varying from 65% to 85%. As an average, you can consider 75% or 0.75. Okay. From this equation, you can find power of pump will be rho G Q H divided by 1000 into efficiency. Rho, you know, 1000 kilogram per meter cube. G, 9.81 meter per second square. Pump flow rate, we know that in liter per second here. But we need that in meter cube per second. So liter per second divided by 1000, you can convert that in meter cube per second. 1 meter cube is 1000 liter. So liter divided by 1000, you can convert that into meter cube. Pump head, we already know pump head is 29.28 meter. Now, efficiency of pump, we can consider that in percentage. Sorry, normally 65 to 85 it will vary. I'll be considering as an average 75%. Now, the power of pump will be, okay, rho G Q H divided by from watt to kilowatt conversion, 1000 into efficiency. So if you are doing manually, efficiency you can keep a 0.75, 0.95 kilowatt. 0.95 95 kilowatt, 1 kilowatt pump. But we need that in horsepower, pump HP, shaft power. 1 HP is equal to 746 kilowatts or 0.746 kilowatt. Correct. So that's why this kilowatt divided by 0.746, we can convert that into horsepower. Kilowatt divided by 0.746, you can convert that into horsepower. So this is equal to this value. Sorry. It's equal to this value divided by 0.746. So you're having a pump of 1.28 HP pump unit. 1.28 HP. Clear? This is the way we are calculating the hydraulic. So real hydraulic calculation will take some time. Okay. But suddenly if you want to calculate material loss, total length you can take multiplied by head loss. Fittings loss, 50% of which one? Material loss we can consider as fitting. Static head P is equal to rho GH. With respect to the height, you can find. Residual pressure 5000 Pascal. Correct. Accordingly, you can, if you want to do that fast by thumb rule, you can do that. But if you're doing like this, that will be accurate. Okay. So this is also same only. Okay. So now we have to select this one. Which one? The pump by the help of a technical data sheet. Anyhow, now this is just our design in FAB. But in real scenario, if you are working in a company, this requirement will be sending it to the supplier. Supplier will give you a technical data sheet. From the technical data sheet, we can find it. Okay. But how to select a pump? By the help of a technical data sheet. So I'll be selecting a technical data sheet after the design. We can select pump technical data sheet. We'll be getting this from the manufacturer. Let's say from previous selection, for example, here you can see we have designed a pump with 28.24 meter and the means pump head will be 28.24 meter. The flow rate will be 61.2 liter per second. Okay. Pump selection we'll be doing by the help of a curve called pump curve. We'll be selecting by the help of a pump called pump curve. Pump curve will be like this. X-axis will be having flow rate. Y-axis will be having pump head. Is having different curves like that. As per our flow rate and head, where we'll be getting the perfect model, that model we will select. Pump selection we'll be doing by the help of pump curve only. Here you can see this is a pump curve with a different model. So this is by manufacturer is Ebara. Model number is CSA-CNA. And this is working in 50 hertz electricity because this is important for VFD selection. For RPM adjustment, we need variable frequency drive. This is a pump standard. And RPM, rotations, minutes right to mine, RPM, no, rotations per minute is 1450. The specific gravity of water is 1, viscosity of water is 1 centistoke, just for reference. But this one, here you can see, pump impeller diameter, minimum impeller diameter 254 mm, maximum impeller, because pump impeller only when it is rotating, it will be delivering the water. Pump is having a minimum impeller diameter for this model, 254 and 307. So that's why in this chart, they have provided 254 impeller dia curve, 266 impeller dia curve, 280, 293 and 307. All the range of this model they have provided. X-axis, flow rate they have provided in meter cube per minute, US gallons per minute, imperial gallon per minute. Y-axis, pump head, they have provided total head in meter, total head in feet, and pump efficiency as well. We have to select this one, but our design is in liter per second. Liter per second, we have to convert into either meter cube per minute or US GPM or imperial GPM because liter per second is not there in X-axis. So we have to convert this. Okay. We can. So like liter per second is how much? Liter per second is some previous design, 61.2 liter per second. 61.2. So liter per second, you can convert into meter cube per second. Correct. means liter per second divided by 3600, sorry, 1000. Liter per second divided by 1000, we can convert into meter cube per second. Now you can convert that into meter cube per minute. Correct. So meter cube per second multiplied by 60, we can convert that into meter cube per minute. Now I have to convert that into US gallons per second. Then US gallon per minute. Imperial gallon per second. Imperial gallons per minute. 1 US gallon is 3.78 liter. Okay. So liter per second divided by 3.78, you can convert that into gallons per second. US gallon per second multiplied by 60, you can convert that into US gallons per minute. Okay. 1 imperial gallon is 4.56 liter. 4.56 liter. So liter per second divided by 4.56, we can convert that into imperial gallons per second. Imperial gallons per second multiplied by 60, you can convert that into imperial gallon per minute. Okay. Fine. So in chart we are having meter cube per minute, US gallon per minute, imperial gallon per minute. So we need data in US gallon per minute, imperial gallon per minute. So 61.2 liter per second is 3.672 meter cube per minute, 971 GPM, 805 imperial GPM. Which one you can select? Anyhow, if you are selecting US GPM or imperial GPM, the difference is US GPM 250, 500. Our requirement is how much? US GPM 971. 971. This is 750. 1000. Somewhere here you'll be having 850. See, that's why. Since the gap is like nearly 250 gallons, when you are plotting like a 971 or something, it will be difficult. That's why where we are having less value. Out of this imperial gallon per minute, US gallon per minute or meter cube per minute, very less value is coming on meter cube per minute, 3.672. Decimal, very less decimal difference only. Less value, so error will be less. So I'll be selecting this meter cube per minute, 3.672. 3.672. Here you can see this is 0, 0.25, 0.5, 0.75, 1, 1.25, 1.5. So difference is 0.25 meter cube per minute. We need like a 3.7, correct? 3.67. So this is 3, 3.25, 3.5. This is 3.75, 3.67, somewhere here. So from this point, you can make a straight line. That will be coinciding here. And what is our head? 28.24 meter. This is total head in meter. 4 meter, 8 meter, 20 meter, 22 meter, 24 meter, 26 meter, 28 meter, 30 meter, 29 meter, somewhere there it will come. We need 28.24. So 28.24 will be coming there. When both these lines are coinciding, see, when it is coinciding with this curve here, impeller dia 254, you can't select it because head is getting like 860, just 18 meter only. We need 28 meter. So our coinciding point is here, just above what model number you are having, not below. Below you will not be satisfying it. From the coinciding point, just above what model we are having, that year you have to select what model. Impeller dia 307. So these 3 models are not possible, 4 models. And you can plot it, what efficiency will be getting. Efficiency will be getting between 70 to 80% of efficiency. If you want to find the pump power, SP for this model and all, you can make this drop down. For impeller dia 307, you can select this curve as a reference. All the other impeller, you can find this as a reference. So this is our coinciding point. From this point, you can make for this selection, pump will be having like a kilowatt of between 20 and 30. Let's say like this is 25 kilowatt, nearly 23 kilowatt of shaft power, not electrical power, shaft power, and also nearly like a 30 HP of approximately 30 HP of shaft power. Okay, now this power is not mandatory, but pump model we need. What impeller you have to select? From the head, different models are available, but we will be selecting for 301. Now we can give the order for this selection. What pump we will select? Then Ibarra, the model will be Ibarra. Model will be Ibarra. Model number CSA CNA. Okay. 1450 RPM. Then impeller dia 5307. Flow rate 61.2 liter per second means, or 3.672 meter cube per minute. Head will be 28.24 meter. You have to order when you are purchasing this item. This order you have to provide. Accordingly, we can purchase this item and we can install. So this is our design, and this is a selection. But as per our design, if you want to select the machine, our requirement, we have to send it to the supplier. Supplier will be giving you the perfect model technical. Supplier will do the selection. Which manufacturer or which supplier is providing the pump, they will do the selection, but we have to verify it. You should know how to select it, right? So accordingly, you can select your pump and you can install that pump.